Today we're very happy to have Mainiero visiting us from UT Austin to tell us about the joy of watching your Bps states grow.
Oh, yeah, thanks for the invite. I really like your elevators. When I first got into it, I sort of looked around to see who was announcing all the numbers or something. It sort of scared me. I hope she's paid for it or something. But, all right. So this talk is, well, there's going to be some talk of supersymmetry or whatnot, and I don't know how familiar everybody is with n equals 2 supersymmetry, but you don't have to be an expert in the field to understand the main results. So, so what do I mean by watching Bps states grow up? Well, if you don't know what a Bps state is, that's okay. I'll talk about it in a moment. But by growing up, I mean, and I'll make sense of this in a moment, both in number and size. And if I start writing small, you can't see, let me know. So, can everybody see this?
Yeah.
Yeah? Okay, so let me start out with the main physical results. That I'll be talking about. At certain regions, of vacuum moduli, for 4-dimensional SU3, n equals 2 super Yang mills. There is a density of states. I'll write DOS for density of states that grows exponentially with the mass. Okay. And the second result. So this first result we stated in a paper with Dmitry Galikov, Pietro Lanhi, and Greg Moore. The name of this was something like Wild Wall Crossing and Bps Giants. And so the giant part is part of this growing up thing I'll talk about in a moment. And the second thing is the Vps Indices. And so what is this thing? I'll talk about it a bit more. It's a weighted count of what are called Bps states. Kind of basic Bps states in a large class of n equals 2 field theories are completely determined by algebraic equations. And if we have time, maybe I'll have a moment to make sense of this. The idea is that you can write down some generating function, and from this generating function you can extract the number of Bps states in the theory. And this generating function will satisfy some algebraic equation.
What's a weighted
count? You're familiar with a sign count, like
what?
a sign count of something? Like instead of counting, so think of a supertrace over some Hilbert space, and I'm not taking the supertrace of the identity operator, I'm taking the supertrace of some operator that could be like +1 or minus some, yeah. So, yeah. This is like a weight index of some sort, yeah. Okay. And the cool
So
thing
you
about
guys
these,
looked at the consequences of this results in the path integral quantization of these theories, you know, I mean, like partition function, computations, things like that, or
Yeah. So I'll mention in a moment that this means that there's some sort of Hagen-Orn temperature to the theory. some sort of limiting temperature.
I see.
And so you expect sort of a phase transition
I see.
at that temperature. Yeah.
You'll tell us about it. Okay.
Maybe I can tell you afterwards a bit more. Yeah. Okay. The cool thing about these algebraic equations, though, is that naively, if I were just to say that there's some algebraic equation that you can extract these Bps states from, and I give you some random algebraic equation, these algebraic equations imply that this exponential density of states, so the density of states increases like e to the constant times mass, is generic. It's a generic phenomenon. Now, I mean, it's not necessarily the case that any arbitrary algebraic equation will appear, so this is sort of just a naive expectation. So it's not, what I'm trying to say by this is it's not surprising from this purely mathematical point of view that you're getting these exponential degeneracies. Okay, so why would you care about any of this? Well, I already mentioned that there's some sort of limiting temperature to the theory. There's some negative temperature. Naively limiting temperature, but you should really be thinking about phase transitions at that temperature. Well, the second thing is that just using standard thermodynamic arguments, there seems to be a paradox. Naively. And I'll talk about this in just a moment. The idea is that you use some standard thermodynamic arguments for field theories. You just assume that you have some sort of field theory, and then you try to figure out what does the density of states look like as the mass increases, and one of the results is that it can't possibly be exponential. So there has to be something wrong with that argument. And we'll talk about that in just a moment. The third thing is, and it relates to this first point, is that there may be infinitely many different Hagedorn temperatures. Yeah, I shouldn't write too far down this. SU3 superunits. So everything I'm talking about is n equals 2. So if I write superunits, I mean n equals 2. Okay. So this means that you can think of, there's just infinitely many different temperatures that you can extract from a theory that seem to be limiting temperatures. Right? I mean, the idea is that you can think of different, if you think of it in terms of phase transitions, a different sector of the theory undergoes a phase transition at a different temperature. Okay, I know very little about phase transitions, so if you want to call me on that stuff, that's fine. I'm just stating mathematical results, interpreting them that way. Okay, so let's first explain why you would think that there is a paradox. So, so there's a naive So let's just start with an arbitrary UV complete field theory. Call it T, and let's say it's d-dimensional. It's on d-dimensional space-time. All right, I'm going to restrict myself to 4-dimensional, but just for fun, I'm going to say I have d-dimensional. And then, so UV complete means that at large energies, so large energies, it's T is well described by a conformal field theory. Well, all I really need is scale invariant field theory. When I say CFT, I really need scale invariant. So let's just take, let me call it C, just to give the theory a name. And so it's a d-dimensional conformal field theory. And so let's heat it up. Let's put C in a box, a volume V, and heat it up to a temperature T. Okay? So then, just by dimensional analysis, because it's scale invariant theory, just do dimensional analysis and expect to get the right answer. The energy in the box is just some constant alpha times the volume to 1 over d times the temperature to the dth power. And the entropy is going to be given by another constant times the volume times the temperature to T-1. So, so if I express the entropy just in terms of the volume and the energy, I get some constant. Maybe I shouldn't use C. Constant times V 1 over d times E to the minus 1 over d. And so the number of states in the CFT at energy E should be some constant times e to the entropy. So I get E times E1 over D times E to the D minus 1 D. Okay. And the result is, because we expect just any arbitrary field theory, this UV complete field theory, to be well described at large energies by the CFT, then if I replace C with the theory T, I should expect the asymptotics are constant times E to some other constant if I fix the volume, E to the D plus 1 over D. Okay, so this is sub-exponential.
I have a question: the index of rate. In your expression for energy is a rate with index 1 over d, and the actually it is 1 over d, just rate.
V1 over D in that one? Sorry, instead of 1 over
The
D.
index of rate is just 1 or 1 over d, because you according with your expression of S equal to something times E.
Yeah.
I found like just naive calculation. It should be the index of rate should be 1 instead of 1 over d, so I think the equations will be consistent.
1 to the 1 over d. Say that again? I didn't quite hear.
Okay, I'm making one.
Yeah.
I think what you just said is that you like take that equation over there, and so you use your two. You have 3 equations.
Yeah,
Use
yeah.
the first 2 to get the third, and he's claiming it's inconsistent. You don't get the third.
First 2 to get the third. Oh, you don't get the third?
Yeah, I mean, you need to choose the index of weight so that you can get the set equation. Otherwise, maybe the index of weight is not consistent.
This is not right here. Yeah.
No, I mean that one. The index of that one maybe not.
Index? What do you
The
mean by the
expression,
index?
The weight.
This or the alpha?
No, weight for weight.
The power, yeah.
I'm sorry.
The power is wrong?
The power should be 1 instead of 1 over d to get.
Oh, it
the
should be
set
1
equation.
instead of 1 over d.
Yeah.
But then,
To get the set equation.
so let's see. Well, you need an expression of energy, so I do need. Yeah, it should be 1. You're right. I'm sorry. Yeah, sorry. Sorry, it took so long. Yeah. Yeah, that's right. Thank you. Right. So, well, I'm trying to tell you that you get exponential degeneracy of states, but yet this heuristic thermodynamic argument says that you should really expect something that's sub-exponential, in particular something in dimension 4, e to the 3/4, right? E to the energy over 3/4. So what's the resolution? Well, one thing that we assumed was that you can actually take the theory and put it in a box of volume V, right? And so we're assuming that all of the possible states of the theory are of finite size. And so if all the states are finite size, indeed, that you should expect asymptotics like this. However, the resolution, so if you want exponential degeneracy of states, or exponential density of states, sorry, the size of the state that contribute to the exponential density of states must grow as energy grows.
Excuse me, how do
Yeah.
you define the size of a state?
You use some sort of semi-classical arguments.
Namely,
Mhm.
can you remind us how that goes?
It's specific to these n=2 field theories. What I'm trying to say is that if these are heuristic, this is a heuristic here. So if I were to take a classical field theory, and I want an exponential density of states, then you can make sense of what the size of a state is, right? It's just sort of like you have a field configuration, right? And that field configuration has some support. It's contained within there's some characteristic size to it. Yeah, think like an instanton. It has some size. And so what I'm saying is that those instantons will have to grow and grow. They're arbitrarily large instantons in the theory. That's the right idea here. Yeah. If you don't believe this heuristic, then that's fine. It's, yeah. Does that make sense?
Well, instanton is a good indication.
Yeah, I mean, that's actually probably the
Mhm.
right analogy. It's more than an analogy. It's some solitonic state. It's like an instant.
Okay.
Okay. So, good. All right, so let's talk about, now that I've put this in your mind, let's contradict it. So I guess I should start from here. So let's say some things about n=2 dimension 4 theories. Not being real specific, just some data that you need to know to understand this Vps index. So what does n equals 2 mean? I'm sure most of you in this room know, but just for the heck of it. So it just means that the Hilbert space is a representation of, so just take one terminology and turn it into another one, the n equals 2 super Poincare algebra. And I was told I shouldn't use this notation because mathematicians like it, but I'm going to use it anyway just to give it a name. Let's just call it P 4/8. The 4 stands for the dimension of the space-time. And the 8 stands for, well, because 8 is 2 times 4. This is coming from this n equals 2. It's the number of odd supercharges you add to the group. Okay? So this is equal to just the Poincare group. And then you add on extra symmetries, or the Poincare algebra. You add in 8 extra generators. And then you add in a complex valued central charge. Okay, I'll call it C. Can everybody see this? Is that?
I memorized.
Huh?
I memorized what you said.
You memorized what I said? Okay, sorry. Yeah. Oh. Maybe that's slightly more visible. I'm calling it. Yeah. I'll try not to do that again. Okay. And so one can show that if you look at any irreducible representation, well, first of all, the representations, E-reps of P 4/8 are uniquely determined by the mass. I guess usually the convention is less than 0, but I'm going to say greater than 0. Just change the signature. Spin, and then you also have this extra thing, the central charge. So one can show in any of these reducible representations that you get this Bps bound, that the mass has to be greater or equal to the central charge. And so a Bps state, or a Bps E-rep, is a one-particle E-rep that saturates this band. And something very special happens when you saturate this bound. So here I'm assuming that the mass is greater than 0. So you don't get something crazy. Something very special happens when you saturate this bound, and that, so generically, the representations of the isotropy group are 8-dimensional. Not just 8-dimensional, depends upon the spin. Let's say spin 0, and I look at dimensions, representations of the isotropy group for P4/8. I get something 8-dimensional, but when I have this bound saturated, then I get something 4-dimensional. Okay? So 4 out of 8 of these odd generators, which I'll call SUSIs, are represented trivially, and which 4 are represented trivially is given by the phase of the central charge. So there's one degree of freedom left over once I fix the central charge is equal to the mass, and that's the phase. So the phase will tell me which four of the supersymmetries are preserved or represented trivially on this representation. Okay, and I'll call this the phase of the Bps representation. All right, so at low energies, the effect of field theory is typically some abelian gauge theory. And so the vacuum of the full theory, which is a choice of vacuum for this effective field theory, actually forms a whole moduli space. The choice of vacuum forms a whole moduli space, and I'll call that moduli space B. It's part, well, B is part of this moduli space. And it's part of the moduli space vacuum. So for each point in B, you get a theory with a different vacuum. And then I can talk about the possible electric and magnetic charges, or even flavor charges, of the particles in the original field theory. And so for each choice of vacuum, there's a different choice of charge. So what you get is over each point, let's say this is B, and have a point U, then what I'll have is a lattice of possible electric and magnetic charges over that point. And this lattice can change. Well, I mean, it's the same dimension, it's the same rank lattice as I vary, but there's a notion of parallel transport from U to U prime on these lattices. So this gamma, this is just the fiber of this map. Is the possible electric, magnetic flavor charges. At the theory defined by U. And this lattice is equipped with a pairing, an antisymmetric pairing. It's integer valued. And you can think of this pairing as sort of, if I took an electric charge and paired it with a magnetic charge, the value of this thing is the angular momentum of the little dion that they form. Okay, so that's going to be integer. If you're familiar with the notion that electric charges and magnetic charges are dual in some sense, this is just the dual pairing between the two. Okay, for those of you who have never seen this, don't let all the notation. Don't worry. If you have a question, just ask.
The vacuum, can you say a bit more about the vacuum? What do you mean by vacuum? How do you define it?
You can think of it as the semi-classical level. If I start out with some Lagrangian field theory, you have to choose boundary conditions at infinity for the fields. And the choice of boundary condition at infinity for the fields is the choice of vacuum.
And what have you taken them here to be?
What am I taking what to be? Well, this is all the possible choices.
All possible choices.
Yeah, yeah.
How do you characterize those choices? Can you give an example, like by how fast they fall, or?
It's just the fields, the scalar fields in the field theory, will go to some constant as they go to infinity.
Indeed, yes.
And this constant is precisely the value of this. So there's a bunch of scalar fields. So for the example, yeah, here I should do an example. This example is probably not going to help what I'm saying. So let me just put it this way. This picture I'm drawing here there are two scalar fields in the theory. And so each point here is just a pair of constant values for that scalar field.
They are in the joint of SU3, are they? No, you're taking into
well, here I'm looking at the
one.
Yeah, I'm looking at the low energy field theory, which is yeah.
The
I mean that
are scalar, they're fixed at the boundary.
yes.
And what about the vector field?
Those typically, just by Lorentz invariance, those have to go to 0 typically. So the vacuum is entirely characterized by just the expectation that it's a scalar.
Thank you.
Yeah, these are Lorentz invariant vacua. Yeah. In fact, there's something called supersymmetric. Well, let me not say something. I'm probably going to say something wrong. So let me just say Lorentz invariant vacua.
Don't say it.
Yeah, so an example that probably some people in this room actually know is just SU2 super Yang mills. Of course, it's just N equals 2. This is the example studied by Cyber and Linton back in 94. I was like 8 or something. So that's how I try to remember. Yeah.
20 years.
Yeah. So they studied this example, and they found, well, the Coulomb branch here is just, you can think of it as just the complex plane. So it's a picture just like this. And then they had this this crazy thing where the lattice of charges, the way you got it, was that you think of you know what an elliptic vibration is, or you just think of like a bunch of tori, a family of tori parameterized by this base. If you don't know what this means, don't worry, it doesn't matter. But for those that do, I'm just recalling. And the lattice is precisely the homology of the torus. Maybe I should. Okay. And I drew these lines. I'm going to explain what these lines mean in a moment. Okay. So this is the picture. And now with this data, I want to ask. So I'll come back to this example in a moment, and I'll describe what these lines mean. Let's just define the index, gamma u, to be the weighted count of Bps states, and the theory. Let me call it TU. So that's just the theory with vacuum defined by U. Okay, and charge gamma. Bps states in the theory of charge gamma. Okay. So here I'm considering these dyadic charges. They can have both electric and magnetic charges. That's what this lattice is. In this example, with these tori, the charge lattice over each point is Z cross Z, and you can think of one Z component as the electric charges, and the second component is the magnetic charges. And if you know a little bit of topology, what this pairing is between these two things, it's just the pairing on homology classes. But if you don't know that, then it's just think of it as this angular momentum formed by these diamond states. Okay. So the cool thing about this index is that this omega gamma u is piecewise stable as we vary u, and I'll make sense of that in a moment. What that means is that most of the time it's stable. If I go from one point to another one, the number of BPS states of the charge gamma is the same, right? The number, this weighted count is the same. That's what I mean by number. But then there are walls. They're usually called walls of marginal stability. Where the index jumps. So going back to this example here, there are two walls in SU2 super-Yang mills. And in this interior region, this is why we should use colors. In this interior region, there are two charges, gamma 1 and gamma 2. And this index is +1. There are only two you can think of them, there's only two BPS states in this interior region. This is the strong coupling region of the theory. And outside on the weak coupling region, there are infinitely many gammas, oops, sorry about that, with omega gamma u equal +1. And then there's one gamma with omega gamma u equals -2. So what do these +1s and -2 means? Well, whenever you have something called a hypermultiplet, which is like the n = 2 analog of a spin 1/2 particle, you will get index +1. Whenever you have something called the vector multiplet, which is the n = 2 analog of just a vector field, you will get -2. So there's one sort of, this is super-Yang mill, so you expect there to be a vector field there. That's precisely what you're seeing. And then you see all these sort of solitonic states with hypermultiplets. Hypermultiplet charges. Then when you go to the strong coupling region, you only end up with two hypermultiplets. Okay. And these little nodes here are where some BPS state becomes massless. And these are the walls where that index jumps. Okay. I'm probably. Okay. So, I just wrote that. Let me move to this one. So, it's nice that these things are stable, but it kind of stinks that they jump all over the place as you vary this parameter u. At least it's staying for a while. But now people understand how this jumping occurs. And in fact, jumping behavior is well understood. So that if you know the count of BPS states at a particular point, we'll call it U star, and you know all the walls of marginal stability, both are tough problems. So this is just in principle. You know these two pieces of data. Then by a result of the mathematical literature, a lot of things have been done in the physics literature before this came out, but this was the killer. Kontsevich and Soidelman, these two mathematicians, came up with a little formula. I'm going to attribute it to Gaudo Morinitsky, but I think there's a lot of work that's been done before them on this sort of thing, but this is where it was finalized. You can figure out the indices for all just by applying this formula. Okay. So the nice thing about this index is it gives you a handle on how many actual BPS particles there are in the theory. So remember, this is a weighted count, but what about the actual count of particles? Well, that thing goes crazy as you vary u in principle. You don't know if it changes. But it gives you a lower bound. So let's take charge gamma u. Let me take n to be an integer. And then 4 times this index, 4 times the absolute value of this thing, is less than or equal to the actual number of BPS states of charge n times gamma. I missed a piece of data. That's okay. I'll just keep going. And so this is less than or equal to the number of states of mass m, which is n times. So I'll define what this z is in a moment. Okay, so one piece of data, I'm sorry about this. One piece of data that I missed for these low energy theories was that there's a function of the charge lattice of C. And the idea is that if you know the electric and magnetic charge, if you know the charge of a particle, you know its central charge. Okay, so there's a function that takes in the electric and magnetic charge and outputs the central charge of the particle. And now because we're talking about BPS states, the central charge, the absolute value of the central charge is equal to the mass, right? That was the definition. And this function is actually a linear function. It's a linear function. So that means that the mass of a particle with charge n gamma is the absolute value of Zn gamma. But because Z is linear, that's just n times Z gamma. So this number n is proportional to the mass of the particle. That's the idea. If I take n times a particle of n times gamma, I get something that's n times, has a mass n times the original thing. So that means that omega n gamma, if we use the naive prediction on density of states, this thing can grow at most as fast as some constant times e to another constant, n to the 3/4. Just by using, so I'm translating it to the language of density of states. I have this inequality. Okay. I'm just going to go back here. Okay. So a question is, how do we compute this omega? And so I'll just say some names. One sort of technique is to use what's called the Bps Queries. It's just a name right now. And this technique requires partial knowledge. Of the Bps spectrum already. But from that partial knowledge, you can extract the entire spectrum. And the second technique, spectral networks, finally get to say this name. This works in what are called theories of class S. This is a large class of n equals 2 field theories. Maybe I'll say a word about it. These don't require partial knowledge of the spectrum at a particular point. Okay. So this is one of the techniques that you can use to actually find the exponential degeneracy I'm about to talk about. How strict is everybody? Just so I know, I can end right, but
Yes, let's go ahead and end by 3.
okay. So let's talk about results that you can get if you use Bps quoters. So there's something called the M-Kronecker quiver. So if you suppose that the theory defined by vacuum U has 2 Bps hypermultiplets. So that means that you already know there are 2 charges with omega of gamma 1, U, omega gamma 2, U equals plus 1. Then the picture of this quiver, you can draw this little picture. I mean, it's meaningless to you, but I just want to draw the picture right now, just to show you how these diagrams look. You draw a quiver whose nodes are labeled by the 2 hypermultiplet charges. And then the arrows between the quiver are given by this intersection pairing. So let's say this was some number m. That's a positive integer. And then I would draw some m arrows between this. So that thing's called the M-Kronecker quiver. And in the math literature, you can use some techniques to show that if you know the theory at this point has a quiver that looks like this, or contains a quiver that looks like that, whatever that may mean, then there exist infinitely many Bps states. And in fact, there's so many that if I drew, so here I'm going to give a picture of the argument of Z gamma. So these are all, this is a picture of I'm going to draw a ray whose slope is the phase of the Bps state. So for every Bps state, I draw a ray. Its slope is the phase. And so here's the one corresponding to gamma 1. Here's the one corresponding to gamma 2. And then there are actually, so for every particle, there's an antiparticle. So this diagram has a sort of mirror here. There are actually a whole, there's a dense region right here. So there's some subset of this arc. And for each point on this arc, you get at least one Bps state. So there's a lot of Bps states here. Okay.
Would you please give some particular value of the arc Z gamma in the dense region?
So
Would you please give some particular values of the arc Z in this particular region?
Give a particular value?
Yeah.
It depends upon the point u that you choose. Oh, give a, yeah, it depends upon that point.
Is it quantized or
No.
No.
It's an arbitrary.
continuously distribution?
There's only countably many possible values.
Countable?
Yeah. Because there are countably many charges, so there can only be countably many possible phases. But the cool thing is that if you look at the particle, so this guy, gamma 1 plus gamma 2, will have an argument that lies right in the middle. And if I look at the Bps index of this thing, this has asymptotics that go like, there's some sign here, times some constant that depends upon m, x to the minus 5 halves, e to another constant. And so you get this exponential degeneracy. Right? So Greg Moore knew about this, and he knew about this thermodynamic argument, and so he postulated that there can be no possible way where you start out with a theory where at some point on the Coulomb branch, the description is very simple, and cross a bunch of these walls to get something that has the M Kronecker quiver. Because if you had the M Kronecker quiver, then you'd have these this exponential degeneracy, which violates this thermodynamic argument. But we know now that the volume has you can have states that this volume grows. That violates that. So, but you can show, so for SU3, super Yang-Mills, there's a point, U, where there's only, I think there's something like 6 Bps hypermultiplets. It could be 12 particles and their antiparticles, but it's 6 or 12. But then you can show that you can cross, this wall crossing phenomenon happens. As you vary u, there's another point, we'll call it u prime, that has the Kronecker M. Bps equivalent. And so you have to have this exponential degeneracy of states. Okay. So, let's see here. I think that made the punchline. I could talk about spectral networks, but then I'd run into time. So I think if you have questions about that, there's another technique you can use to actually derive this equation called spectral networks, where we figured out this. The way you do that is you can for each point u, there's a technique for writing down some differential equations. The integral curves of these differential equations draw some graph, and there's a combinatorial technique from that graph. This graph sort of represents a Bps state, and there's a technique to use that graph to actually calculate these Bps indices. And so we actually found a graph that gives you precisely all of the Bps indices for this particular particle with charge gamma 1 plus gamma 2. So there's 2 techniques in which you can verify this exponential degeneracy. Okay, but I should end there.
So the first way you described getting to this point, the exponential growth, was the starting point somewhere in the strong coupling region, the SU3?
Yeah, there's a strong coupling point.
And
we don't know what the other point is. We haven't thought that much about it.
do you know, like, is what value of the coupling is there?
Yeah, you can write down the Severgreen curve like this explicit thing. So
I don't have a sense of whether it's
No, I don't, yeah, I don't know off the top of my head, yeah.
How many walls do you cross to get from?
It's less than like 10. Yeah. But the thing is that I'd expect going out into the weak coupling region of this, you should also probably see this exponential degeneracy. I mean, it seems to be most places on the, if you move out of the strong coupling region, like you hit all these walls and it just gets worse and worse. Like the spectrum grows and grows and grows. So.
Do you think it's possible to get to this point from weak coupling with passing through infinitely many walls?
That's a good question. I don't know. No, this part of the story I haven't. This part of the story was mostly done by Greg and his students. They have a nice program that runs this wall crossing procedure. So I haven't given much thought about that yet. And I don't know. It's so crazy. I have no expectations. Yeah.
All right. Let's thank the speaker again.